as promised, I'm going to go back and I'm going to work these problems that we did in the homework sets for the first test. I know the first test is behind us, but I would still like for us to, if you had any questions about those problems, to be able to go back and work them. I think the skills we learned in those homework problems were very useful to us. I'm a little concerned that, are you hearing this? Hello? Hello? Okay, yeah, it's popping up there. Never mind. All right, so, okay. So let's start with problem 1 out of homework set 2.1. The first problem there was problem 2, a point MN in the plane is a lattice point if both coordinates are integers. And so what we wanted to prove is that the number of lattice points inside a circle centered at the origin, 0, 0, is a number of the form 4k plus 1 for some integer k. All right, so let's start off, and this is where it may behoove you. Sometimes, you know, it helps to put a little diagram in things, and so let me start with a little picture. You know, if we're looking at this, and we have a circle, let's see if I can freehand draw a circle. Hey, that's not really bad. I mean, it could be much worse. If you think about this, we've got one point that would always be in here, and that is this center point at the origin. And then whatever the integer kind of things are that fall in there on the axes, okay, that'd be a multiple. I should probably let me do the center one in blue, because it's the only single that we've got. Everything else is going to appear in multiples of 4. Right? And then if we look, I don't know how many we have in each quadrant, but if we have some there, exactly the same things will happen over here, right? So it does kind of make sense. This answer, we just need to write it up. Okay, so let's do that. And I will start this with just a statement of the equation. The equation I'm not sure this is really crucial. Can I get by without the... Yeah, because I want to talk about the radius. So let me go ahead and say it. The equation of a circle centered at the origin is x squared of radius r plus y squared equals r squared, and that's for some positive radius r. Okay, so the origin is always in the circle. And all positive integers, let me call these m. No, hold on a second. 1, 2, ... m Better just put less than. Because inside, we didn't want to talk about the boundary, did we? Less than R. We have the points on the axes. It's just said plus minus M0 and 0 plus minus M, which is 4M points. If there are, I don't know how many there are, but however many points I have in the first quadrant, Q points inside. I'm going to start moving back over here now. Inside the circle in the first quadrant. Of the form AB. We also have, you'd have a minus AB. You'd have A minus B. That's going to put you down in the fourth quadrant. This one was second quadrant, that one's fourth quadrant. And then third quadrant, minus A minus B, which is 4Q points. And I should say up here 0. M is I'm assuming a positive thing, bigger than. Okay. So so we have a total then of the 1 and then the 4M for all those things along the axes and then the 4Q, which is equal to 4 times M plus Q plus 1. Where M plus Q is most definitely then an integer. Okay, and that's what you had to show. QED, put your little box, whatever it is, there you go. Okay, now let me say one thing about these solutions. I've decided not to post them as PDF files because I want to encourage folks to actually watch me work it. Okay, so if you're willing to commit the time to watching the videos, then you can get these, or if you figure out a sneakier way, that's fine, or fast forward up and you can do it. But I don't want you simply printing them out. I don't think there's a lot of value to that. So I'm going to forego posting these as PDFs. You will have the video to go by, and I think that's sufficient. Okay? All right, so there's the first one. Let's go to the second problem, which is problem 3. It says let A, B, and C be integers, and let L be a line. AX plus BY equals C. So you get that whole set of points on the line. Prove that if L contains one lattice point, then L contains infinitely many lattice points. Now, I want to step inside this, the one thing that doesn't work too well when I have one piece of paper like this is that I have a hard time kind of showing you the scratch work, but let's do the scratch work on this. Okay, kind of off here to the side. What I would be thinking is this. Okay, what's the slope of this line? And then can I find, let's say I've got 1 point, can I find the other points and prove that I've got all these integer points on the line? So let's look at this line. If I'm solving this, putting it in slope-intercept form, this is by equals a negative ax plus c. And that means that y is a negative a over b x plus c over b. Now the c over b I'm not too concerned about, but the slope I am, right? So the way you can think of this is if I have 1 point, let's say I have m, okay, for my x equals this. And then if I take, and you know, this is rise over run, right? So think about, maybe you can put the negative with either one, but if you think about the negative a in the top, then that's the rise and affects my y-axis, and then the b affects my run, my x-axis. So if I have m and then I add some multiple of b, and maybe this is n, and I add some multiple of a negative a, okay, then what should be happening here is that, okay, I jump that run, that rise, whatever it is, and then it's pretty easy to see that these are both going to be integers, right? If k is an integer. So that's my thinking on this, is that, okay, let's assume there is a point, okay, and then let's show these other points. Now what we do have to demonstrate is that these points are actually on the line, but they will be because we're playing our cards right here. We've calculated the slope of the line, so it'll work out. But we'll have to test that in the proof, okay? So here we go. The proof is, okay, it says if it contains one last point, so let's pick one. Let's let, and I'll stick with my notation over here, mn be a last point on the line L, okay? By definition, that means that m and n are integers, okay? And consider the points, and I'll do the m plus kb. This is what we said earlier, right? And then the n, and actually that's minus ak, right? Or ka minus ka for all integer k. Okay. Then plug those points into our equation of the line. So we've got a times, oh, and one thing I should say is since that is a lattice point on the line, maybe I should say that before I do this. Note that since mn is on L, then a m plus b n equals c. In other words, if I plug those in for x and y, it satisfies the equation. So now consider, and let's plug our infinite set of points into this equation. So I've got a times the x, which is m plus kb, plus b times the n minus ka. Okay, now don't write c equals c. We've got to prove that. Okay, that's something that we've got to establish. So instead, let's go through and distribute our variables here. So I've got am plus k times ab, and then I've got plus bn, and then minus kab. Well, pretty easy to see that those are going to disappear, right? And so what I'm left with here is am plus bn, but we just established that that's equal then to c, right? Therefore, this infinite set of points is also on the line L. Okay? All right. Important that you not put the equal C up there. I harped on a few of you on the test, and I've been doing it at the board too. You have to establish that. You can't just put that in there and then start working down both sides. You can't do that with equals. Okay, you have a chain of equals where you get the left side look like the right side or something like that, but you can't. And I'll tell you another thing that another reason to avoid that is if you're saying that, number one, you're assuming what you're trying to prove, but number two, you're tempted greatly because you think it's equal to move something off one side onto the other, and you absolutely cannot do that at all. Okay. All right, so that was number 3. Let's go to number 4. This is the point where they ask us to circumscribe a circle A by a square B, and then circumscribe the square B by a circle C, and then prove that the area A contains exactly half the area of the circle C. So what we probably want to do here, and I'm a big believer in diagrams and pictures if it helps, is just kind of draw the picture. We've got a circle A, and then we've got a square B, and then we've got another circle C. Okay, so let's start by looking. This will say maybe this is radius R. Okay, so here goes our proof. We would say something to the effect, let the radius of circle A be R. Then we know that the area of circle A is pi r squared. By the way, point of information, Friday is Pi Day. It's March 14th, which we always kind of end up celebrating as Pi Day. It'd be really cool next year on Pi Day because it'll actually be pi out to 4 decimal places. 31415. Yeah, pretty slick. Okay. All right. So now let's calculate the area of this square. And again, what I would go through and look at on the square is that this has sides of length, oops, I'm getting ahead of myself, 2r. If the radius is r, then the length of one side, which is halfway across, all the way across, is 2r, right? The length of one side would be the same as the diameter of the circle. Then the square B has sides of length 2r, and really, I mean, the thing I guess we could simply go by here, if we think of this as r and this is r, what we need to find out next is out to that point, because that's going to be the radius of our circle C. You can look at the, it's 2r by 2r and then do the diagonal across there. But it's okay. It's a right triangle, and it's also a reference triangle for us, right? The 1, 1, square root 2, or the, I forget how we did that, square root 2, square root 2, 1, 2, however you want to do it. So, okay. So, then the, oops. Radius of circle C is square root of 2. Then notice how we're just chaining together a bunch of then statements. Oh, well, if that happens, then this happens, then this happens. Then the area, and this is what we're concerned about, right? Is comparing the area of circle A to the area of circle C. So this is pi. Oh, I'm sorry, I told you wrong. It's not square root of 2. It's square root of 2r. Right? If this is 1r, then that's square root of 2r. My bad. So this area is then pi, and now the radius squared, which is pi. And then you square the square root, you get 2 and r squared. So this is 2 pi r squared. Then the area, well, I can use it then, use my notation. One half of area C, oops, that's not how I wrote it, C is 1/2 this 2 pi r squared, which the 2's just get rid of each other, r squared, which is the area of circle C, circle A, sorry. And that's what we had to show. Boom, boom, boom. Okay. Hopefully it's all going well for you. These are, for the most part, direct proofs. The final 3 are when we talked about the floor function, and which I defined in one of the lectures. So let me get to that first one. Here we actually have 2 inequalities we have to prove. One is that the floor of x plus the floor of y is less than or equal to the floor of x plus y quantity, and then show that that inequality, that amount, the floor of x plus y quantity, is less than or equal to the floor of x plus the floor of y plus 1. So if you remember how this came about, we always say if we're looking at a number and we take, you can always express it as its whole number part, which is the floor, and then the decimal part, which is some number between, including 0, and less than 1. Okay? So that's the first thing I would do, is look at x and y and say, okay, let's write these involving the floor. There exists, what are we going to use, mn, where these things are greater than or equal to 0, but strictly less than 1, such that if I look at x, I can say, okay, that's the integer part of x plus the decimal part, and I can look at y and say, okay, that's the integer part, which is the floor, plus the leftover business. Now, I'm thinking really in terms of positive when I think about the integer part. If we were looking at a negative 2.5, for example, this would be a negative, the floor part would be a negative 3, right? So it wouldn't really be the decimal part. Or I'm sorry, it wouldn't really be the integer part, but it would work the same function, and then we'd have 0.5 as our add-on, our little number between 0 and 1. Okay, so, but at least the way to think about it with positive real numbers is that that floor is like the part in front of the decimal, and then the number is the m and the n. That's the part after. Okay. Now it's easier with these things to break them apart than it is to put them together. So I'm actually going to start right in the middle of this, and I'll prove this one first. I'll prove that this is greater than or equal to this, and then when I'm done, I'll go back and prove this is strictly less than that. So let's do that first part. Consider, okay, the floor of x plus y. Now, this is equal to, just direct substitution, the floor of x plus m, that's the x, plus the floor of y plus the n. Okay, now if you notice, what I need is in here. This floor of x plus floor of y is there. I've just got some extra stuff. Throw that extra stuff away. Okay, that's going to make it possibly bigger, possibly equal. If m and n are both 0, it would be equal. But if I just throw the m and n out, then that's greater than or equal to this. And, oh, I didn't mean to write n, my bad. That's y, excuse me. And that's an integer. So the floor of an integer is just that number. Okay. So that's the first part. Okay, that's the first inequality. And now let's look at this one. Again, I'll do this. Okay. And go through and see if I can get inequality where this is bigger. So also, if I look at this, and I'm going to repeat this step, okay, then, okay, what can m plus n be? Well, if they're both 0, it'd be 0. If they're both near 1, this would be near 2, right? So what I can say is, and I'm used to having, I want this little thing dangling out here between 0 and 1 so I can undo my floor function. So this is the same as the floor of x. Well, actually, I'm going to insert a 1 here. Okay, so that's going to make it bigger. Plus, and let me get these two things together. But what I'm really saying is that m plus n is strictly less than 1 plus k. All right. For some k, between 0 and 1 could be 0. You know, if it's 1, if m plus n is 1, it'd be equal, and k could be 0, right? Okay. But k being close to 1 means that this would be close to 2, and that's what we said about m plus n, okay? And so now this is my little decimal part, if you will. This is now my whole number. So this is then the floor of that is just that. And because we have this inequality in here, that's strictly, not strictly, that's less than or equal. So we've actually combined it, therefore, what we're trying to show. Okay, that is less than or equal to this, which is less than or equal to the same thing plus 1. You know, the real question there is, you know, the x and the y, you can split them up, or they may have decimal parts that add up, but they're always going to be you know, you'll get the number, and then you've got one number out here that'll kind of cap it off. Okay. All right. Good. Okay, so that's that one. Need a little block there. Boom. Good. Let's take a look at 5D, which now we're looking at a product. It says prove that the product of the floor of x and the floor of y is less than or equal to the floor of the product x times y. Okay, I would start this exactly the same way. This is a direct proof. You know, there exists mn between 0 and 1, possibly 0, such that x is the floor plus m and y is the floor of y plus n. Okay? And again, I'm going to start by looking at that product because it's easier to break things out than it is to put them together, at least from my perspective. So let's look at the floor of the product. Okay, now that would be the floor of x, now this is just direct substitution, plus m, plus, oh, and there is one important criteria of this x and y. They have to be positive numbers for this to work. Okay. All right, so floor of x plus m quantity times the floor of y plus n quantity. Okay. So just FOIL this out. You got the floor of x times the floor of y, and then we've got m floor of y plus n floor of x plus m n. And we're looking at the floor of that whole creature. Okay? Now this is the important part. The x and y's and their floors are all positive. Okay? The m and n are all non-negative. I guess I should call everything non-negative. The x's and the y's and the m and the n's are all non-negative. So to make this bigger than what I've got, I just need to take a bunch of stuff out. So I'll take out this. What I'm trying to get is just this, right? So take this out, take this out, take this out. You know, if m and n are both 0, then it's equal, but it's bigger than, in most cases here, the floor of x times the floor of y. Those are both integers. Integer times integer is an integer. And so this is just the floor of x times the floor of y. Okay? And that was it. That's all there is to that. All right. And then lastly, let's look at the one here with the a and the b. And this is an if and only if statement. It says that the floor of a divided by 2 plus, and a and b are integers, a divided by 2 floor plus the floor of b divided by 2 is strictly less than a plus b divided by 2 if and only if a and b are both odd. So the way I would prove this, probably because we have a nice way of expressing odd numbers, is to say, okay, let's assume they're both odd and prove it this way first. And then really we want to start here and prove that way, but it might be easier to prove the contrapositive. If a and b are not both odd, you know, that's the opposite of this one put first, then this is not a strict inequality. Okay? So we'll start off with this side right here and prove this. And then this to prove that, but I'll do it by using the contrapositive. Okay? So here's our proof. Let a and b be odd. Now, what does that mean? Then there exists m and n, integers, such that a is 2m plus 1. I should write and, sorry. And b is 2n plus 1. Okay. Then let's take a look at this. And again, I think it's easier to start with the whole thing and split them out. Okay. It might be easy to show here that what these things are, what the floors of each of these things are to begin with, right? We're going to need to know that. If I look at just the floor of a over 2, then that's the floor of 2m plus 1 over 2, which is m plus a half, which is just m. And if I look at b over 2, guess what? This is 2n plus 1 over 2, which is n plus a half equals n. Okay, so whatever those integers are, when we look at a over 2 floor, b over 2 floor, those are the numbers we get. Now consider, oops, don't need a period. Floor of a plus b over 2. So this is 2m plus 1 plus 2n plus 1 all over 2 quantity floor. So we have here m, and we've got n, and 1 plus 1 is 2, divided by 2 is 1. Okay. But to get the strict inequality, well, take the 1 out of there, right? This is necessarily larger than m plus n, which is m plus n because it's integers. Well, honestly, I could have said this to start with, right? Let me just go back and do that. This is equal to m plus n plus 1, which is strictly more than m plus n, just kick the 1 out, which is the floor. M is the floor of a over 2, n is the floor of b over 2. Okay, so we've actually proven it now from the n part to this. So I'll say that to prove that the inequality implies that A and B are both odd, consider the contrapositive and suppose AB are not both odd. And so it doesn't matter which one, but let's make sure that at least one. It doesn't mean they're both even. It just means they're not both odd. So let's say maybe just one of them's even. So without loss of generality, that's something we say because I could pick A or B, and I'm not giving up. It doesn't have to be one or the other. Let's let A be even. Then let's go back and do our proof, but I'm going to define A a little differently. Then there exists m and n, integers, sorry. Such that A now is 2m and B is 2n plus 1. Okay? Note that, and I want to go through and just get this out of the way, that if I do take the floor of A over 2 now, that's the floor of 2m over 2, which is just the floor of m, which is m. And if I look at the floor of b over 2, this is the floor of 2n plus 1 over 2, the floor of n, oops, that looks like an m, n plus a half, which is just n. Okay? So let's consider A plus B over 2. Okay, now this is just direct substitution, 2m, and then B is 2n plus 1. We're dividing by 2. So 2m divided by 2 is m, 2n divided by 2 is n, and then plus a half. Well, these are integers, and then the half is between 0 and 1. So this is just m plus n, which we just proved this. M is a over 2 floor, and N is B over 2 floor. And you'll notice that all those things are equal. So what we've shown then is that that inequality is not a strict inequality. They can be equal. Thus, the contrapositive it's quicker to say holds. And the statement then is correct. Statement is true. I can't spell for some reason. Sorry about that. There you go. Oops. Put that in another place. Okay. So that's the first, I don't know how many problems did we work. 1, 2, 3, 4, 5, 6 problems. I'll go through and record some more, probably tomorrow. I'm getting a little tired now. It's 10 o'clock or so. But we will pick up there and start doing the rest of them. All right, and I will see you later. Have a good break.